Hello and welcome to Lecture 2 of our course on stochastic modeling of biological processes. Lecture 2 is dedicated to computer simulations. First, let me note that all computer codes for figures from the lecture notes are available at this website. Although some simple stochastic models can be analyzed using only a pen and paper approach, one cannot apply stochastic modeling to more complicated examples without using computers. Thus, our discussion is not only built around mathematical equations and their analysis, but also around the corresponding algorithms. However, we do not assume prior knowledge of a particular computer language. The presented algorithms are all written in a general pseudocode. In the Oxford courses, students are asked to implement examples from their lectures using a computer language of their choice. They have a course covering MATLAB in the first year of their degree. Therefore, Lecture 2 of this course includes a discussion how they can use MATLAB to simulate examples from our lectures. The choice of programming language is not important, but hands-on experience with implementing algorithms from the lecture notes in the computer can improve your understanding of the underlying mathematical methods. In this lecture, we will be discussing how you can write a MATLAB code which reproduces figure 1.2 on page 10. It has the following two panels. The left panel of figure 1.2 shows results of 5 realizations of the SSA A3D3 together with the mean MT, which is plotted as this dashed line. Let us start with plotting this dashed line. It is the solution of the ordinary differential equation for mean MT, equation 1.15, with initial condition m at time 0 is 0. This equation can be solved analytically to obtain this formula. Therefore, we can plot the time evolution of mean MT using the following code in MATLAB. The first two lines specify the values of parameters k1 and k2 new. We use k1 is 0.1 and k2 new is 1. The third line defines the values of time t. It is a vector with entries 0, 0.2, 0.4, 0.6, all the way until 100. The fourth line is our analytical formula for mean m. And the last line asks MATLAB to plot m against time t. Let us now press run and we obtain the following figure. We observe that the resulting plot looks slightly different from figure 1.2a. To get figure 1.2a, I substituted the simple plotting command plot tm with a few more lines to improve the output. I have added a few options to the plotting command, specifying that we will use a black dashed line and its width. The next line says that we will plot the interval 0-100 on the time axis, and the range of m will be interval 0-20. The next two lines will specify labels on each axis. We will plot time on the x-axis and number of molecules on the y-axis. And finally, it is also good to increase the font size. Let us now press run again, and this is the resulting figure, which shows the time evolution of mean MT exactly in the same way as figure 1.2. Next, we implement the SSA A3D3 in MATLAB. We start by initializing our main variables, A, which gives us the number of molecules, and time. We also introduce vectors aplot and timeplot, which will be used for storing and plotting our results. It is good practice to initialize the random number generator. MATLAB uses the following command. Then we get the same sequence of random numbers whenever we run the MATLAB code. This is very helpful whenever we try to identify errors in our computer code, which might otherwise be difficult to find. The main loop of our computer implementation of the SSA A3D3 starts with the command while. First we calculate two random numbers using the command rand. Then we calculate the total propensity function A0. Then we update the time when the next reaction occurs. Time to the next reaction is an exponentially distributed random number computed as 1 over A0 logarithm 1 over R1. And then we use the second uniformly distributed random number R2 to decide whether it was degradation, where we remove one molecule of A, or production, where we add one molecule of A. In each iteration, we store the number of molecules and the corresponding time in vectors aplot and timeplot. This is a MATLAB construction which allows us to add additional entries to vectors aplot and timeplot. The results stored in vectors aplot and timeplot are plotted using the following commands. The first command, hold on, helps us to plot the computed realization of the SSA A3D3 into the same figure as our previous plot, visualizing the mean MT. To plot a plot against time plot, we use the command stairs instead of plot. This helps us to emphasize that the value of A stays constant until a reaction occurs. Let's press run and we obtain the following figure, showing one realization of the SSA A3D3 together with mean MT. We can obtain 5 realizations as plotted in figure 1.2a by using this code 5 times. We have to make sure that we use different random numbers to get different time evolutions of A. The resulting MATLAB code, which plots figure 1.2a, is available on the following website. As the next step, you could try to compute the stationary distribution presented in figure 1.2b. To do that, you could run many realizations of this code to obtain the presented histogram. Please note that you will obtain more efficient codes in MATLAB if you only store statistics which you are interested to plot. Therefore, store the histogram and do not introduce aplot and timeplot to store details of all computed realizations. Otherwise, you could end up with a slower code if you attempt to store and work with unnecessary large data files. If you have any difficulties to calculate the stationary distribution, you can also check the MATLAB code for figure 1.2b on the following website. This brings us to the end of lecture 2, which covered computer simulations. In our next lecture, we will conclude our discussion of chapter 1. We will cover sections 1.3, 1.4 and 1.5 on pages 15 to 29. We will consider how we can simulate general systems of chemical reactions, and we will discuss additional methods for the analysis of stochastic chemical systems. Thank you for listening to our video lecture of Oxford course on stochastic modeling of biological processes.